Alright, this is lesson 74. Today we're going to do a lesson on half-life, which is opposite concept of growth yesterday. So half-life we use a lot in the scientists use it in chemistry, basically. So the classic example of half-life is, let's say you have a fossil with a certain type of carbon or a certain amount of carbon. They could actually date the fossil using carbon dating. They know that a carbon isotope has a certain half-life, and they'll say, like, oh, they'll test the carbon. They'll say this carbon has this many, or this much, or contains this much carbon, and therefore it must be so many thousands or millions of years old. Okay, or hospitals use half-life all the time. Every day hospitals use chemicals, and they use, or maybe when they give you a CT scan, or they give you certain medication, and so the medication that they give you or the chemicals that they put in your body have a certain half-life, right? You don't want chemicals to stay in your body, right, after they put it in, right? You want it to go away, so they have a certain half-life. Or another example is like your drugs that you get at the pharmacy, right? Did you ever notice that there's a expiration date on them? Okay, you might think, oh, it's just drugs, they look the same, but they actually have a half-life and they don't have the same potency as they did when you first bought them. Alright, so that's what we're doing today, and we're going to be doing some conceptual stuff with a calculator, so it's going to be a little bit harder today, but I'm going to show you how to do a couple problems. We'll be using the graphing calculators today, and we'll also be using, or just calculating in general. Alright, here are the steps. If you're on the video, pause it now and write those down. Here we go, numbers number one. A hospital prepares a 100 milligram supply of technetium, which has a half-life of 6 hours. Technetium. Make a table showing the amount of technetium 99M that remains after 36 hours, and solve for how much technetium 99M remains after 75 hours. So, I'm just curious, what is technetium? Can someone Google that while I start working this out? Technetium. So, alright, so whenever you look at a problem like this, we have to work things out, we have to kind of understand what's going on. So, the hospital is preparing 100 milligrams of something, so like a little amount of it, and it has a half-life of 6 hours. So the first thing you always want to do is figure out what's happening in the whole situation, and it's good to make a table. So I like making a table before I start working things out because it helps me understand what's going on. Okay, so I'll just make a table and draw some lines. Okay, and I know when I first make the technetium, or the hospital makes it, how many milligrams is at the very beginning before it even gets old? How many milligrams do they start with? 100 milligrams. Okay, so no time has passed, right? 0 hours have passed, and there is 100 milligrams of it, right? Then I have to think to myself, okay, so there's a half-life, and it says there's a half-life every 6 hours, right? So 6 hours have to pass before I get a half-life, right? So 6 hours will pass, and there's now half of 100, which is 50, right? 6 more hours will pass. Oh, by the way, this is our that's in the first interval. 6 more hours will pass, so 12 hours would have passed, and then there's 25 milligrams. And 18 hours would have passed for 12.5, and so forth, right? And I'm making a table showing the hours that pass and how many milligrams of technetium I should have left. Right? So, and there are intervals for each half-life, right? Did you get an answer what technetium is?
Yeah. It's used for medical diagnostic studies. Several chemical forms are used to image different parts of the body.
Okay. Is that what you got to? Anything else? Okay, so it sounds like they put it into you, swallow it or something, or you...
It's radioactive. Stick through the veins in the armor.
Oh, it's injected into your veins? Oh, that's interesting. So, cool. So they put it in for diagnostics to see if you're okay, or whatever the test is, okay? Anyways, there's a half-life as it goes, right? And thank God, right? Because it's radioactive, you said? Is it radioactive? So they're putting radioactive stuff in your body. Right? You want it to have a half-life, don't you? So that it goes away. You all agree with that? Alright, so the question now we're asking ourselves is, how much technetium remains after 36 hours, okay? So, we know that, I'm sorry, make a table showing up to 36 hours. Then we're going to solve how much technetium remains after 75 hours, right? Does our table go up to 75?
No.
No, we could do that, but 75 is not a multiple of 6, right? You follow me right now? Okay, so now we have to make a graph. So this is an equation that I would use. Is y is equal to I times 1/2 to the 1 over t times x. So I'd start with writing that down. I put n, but I really want it to be x up there. So I is the initial amount. We're using the fraction 1/2 because we're talking about half-lives, right? The initial amount will reduce by half. This exponent, 1 over t, we're saying that there's one half-life for every so many hours. Does that make sense? So there's going to be one half-life for every, in this case, 6 hours. So we're going to, oh man, I went too far ahead. So that's going to be our interval time. Okay? And then n is the total time that we're talking about that passes. But I'm going to change n to show x because this is really like a function that we're going to use for in our calculators, because we could see one answer or we could see all the answers, okay? But in our particular example, we're going to make x 75. So we're going to rewrite this. We're going to say I times 1/2 to the 1/6 times 75 is equal to y. Okay, so now I'm going to solve this. So I'm going to go to my calculator, and I have it as one fell swoop. I'm going to work this out using PEMDAS, right? Orders of operations. So you could all do this along with me if you like. Clear out your calculator in memory. Okay? So the first thing you want to do is PEMDAS. So the exponents are in its own parentheses. Oh boy. Okay? So we got 1/6 times 75. So we're going to go 1 divided by 6, and we get a decimal. We're going to multiply that by 75. We get 12.5. That's our exponent, okay? Now we're going to do 1/2 times 12.5, or to the 12.5 power. We go 1 divided by 2, which is 0.5. Use the exponent power to the 12.5 power, and we get this long decimal. We're going to multiply that by 100. Okay, and we find that there is a small decimal amount of technetium left. Okay, so I get this, and I'm going to round to the nearest 10,000th for my example here. So after 75 hours, there's only a small fraction of a milligram left of technetium. Okay, so that means even if they were to inject this into your body, after 30 or 75 hours, you would have this much left. Does that make sense? Okay. So in comparison to yesterday, we were talking about growth, how money grows. What is half-life? What model is half-life? Exponential growth or exponential decay, right? So we're talking about exponential decay. Okay, so raise your hand if you're going to be a nurse, or you want to go in the medical field, nurse or doctor or anything medical, chemistry, pharmacy. Okay, this is going to be part of your life, okay, is dealing with these kinds of calculations, okay? So this is the kind of math you'll have to deal with, these concepts. So why don't you turn your neighbor, today's Tuesday, let's have the twos talk today. Twos are telling the ones, how did we solve this? How did I organize everything, and how did I solve this, okay? So I'll give you 2 minutes to talk, and you can write this down. You don't have to write the original problem down if you don't want to either. Go. Take that to the side and just, instead of writing 75, I had this equation, 100 times 1/2 to the 1/6 times x power. I could plug this into my calculator. So if you're on the video, I'm going to go to a graphing calculator, so plug this in. Okay, number 2, here we go. Arsenic. Arsenic 74 is used to locate brain tumors, okay? How about that? Can someone else Google, or someone Google what arsenic is used for? Google, what is arsenic used for? Okay. See if there's anything else. Good job, Araya. Pretty quick. Okay, so it has a half-life of 17.5 days. Write an exponential decay function for a 90 milligram sample. Use the function to find the amount remaining after 6 days. Okay, so sometimes you might be an oncologist, right, working with patients that have cancer or might have cancer. That's what an oncologist does, okay? Or a doctor that works specifically with cancer patients. Use the function to find the amount remaining after 6 days, okay? So we're going to use arsenic here. So it's the same example. Now let's, instead of making a table, we're going to make a table again, Adam? Do we have to make a table? Yeah. Let's think about it. How many milligrams are at the beginning of my sample? 90, right? Day 0, hour 0, there's full amount, 90 milligrams, right? How many days have to pass for a first half-life?
17.5.
Okay, so at 17.5 days I should have how many milligrams?
45.
45, right? Half of 90, right?
Yes.
And then at day 35 I should have how many milligrams?
22.5.
Good, 22.5, good, right? So you have to think that way. If that's too hard, make a table, okay? But this time I'm not going to make a table. All right, instead we're going to go straight to write the equation out. So you're going to go write y is equal to 90 times 1/2 to the 1 over t times x. Okay, and we're plugging in all the information that we need, right? In this example, we know that the original amount of milligrams for arsenic is 90 milligrams. Okay, that's how much is in question. We know that it's a half-life, so we have to use this multiplier of 1/2 of this base. Okay, and we know that there's one half-life for every 17.5 days, and we're asking ourselves how much is left after 6 days. Okay, so let's calculate this. Now you could do this either two ways. You could do one foul swoop on your calculator, or you could do it on a graphing calculator. So why don't you calculate that? Check with your neighbor. I'll give you about 30 seconds to calculate that. Go. Okay, so after one foul swoop, you should get this answer: 70.963, 0 milligrams, or 70 and 9,630 10,000ths milligrams. Okay. So let's do this again on a graphing calculator, right? So sometimes in your homework you don't have to put the 6 in. Let's put an x there instead. So let's rewrite the equation on our graphing calculator. But instead of where it said 6, let's change it. Let's put it so it says 1, or let's say it's x right there, right? So we're going to erase that 6, put an x. Let's put that into our graphing calculator right now. Please, go. Everyone's doing this. And I'm going to come around and check to see that you understand how to zoom out in the appropriate place and so forth.